NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve quadratic equations step by step using the quadratic formula. We'll introduce the discriminant, explain the three cases, and finish with a fully worked example. First, let's place an example label. Then, we show the general quadratic equation, ax squared plus bx plus c equals 0. Step 1. State the quadratic formula. The solutions are x equals negative b plus or minus the square root of b squared minus 4ac, all over 2a. Step 2. Define the discriminant. We let capital delta be equal to b squared minus 4ac. Step 3. Rewrite the formula using delta. Now we have x equals negative b plus or minus the square root of delta over 2a. Step 4. Consider the three possible cases for delta. If delta is greater than 0, there are two distinct real roots. If delta equals 0, there is one repeated real root. If delta is less than 0, there are two complex conjugate roots. In this guided example, we will transform a rational equation into a quadratic, and then solve it step by step using the quadratic formula. First, here is the example we will solve. 6 over p equals 2 plus p over p plus 1. Step 1. Rearrange the equation so that everything is on one side, and the right-hand side is 0. In words, bring all terms to the left. The result is 2 plus p over p plus 1 minus 6 over p equals 0. Step 2. Clear denominators by multiplying both sides by the common denominator p times p plus 1. After multiplying, we get 2p times p plus 1 plus p times p minus 6 times p plus 1 equals 0. Step 3. Expand the products carefully. 2p times p plus 1 expands to 2p squared plus 2p. P times p is p squared. Negative 6 times p plus 1 is negative 6p minus 6. Put together, we have 2p squared plus 2p plus p squared minus 6p minus 6 equals 0. Step 4. Combine like terms. 2p squared plus p squared gives 3p squared. 2p minus 6p gives negative 4p. The constant term is negative 6. Therefore, the quadratic is 3p squared minus 4p minus 6 equals 0. Step 5. Use the quadratic formula with it equals 3, b equals negative 4, and c equals negative 6. Substituting gives p equals the fraction 4 plus or minus the square root of 16 plus 72, all over 6, which simplifies to p equals the fraction 2 plus or minus the square root of 22, over 3. Quick quality check. All algebraic steps follow directly from rearrangement, clearing denominators, expansion, combining like terms, and the quadratic formula. The final expression is simplified by factoring the common factor 2 inside the numerator. In this lesson, we will solve a quadratic that contains a parameter. We are told that negative 4 is a root of the equation 4x squared minus ax plus 20 equals 0. We will first find a, and then compute the other root step by step. Step 1. Because negative 4 is a root, substituting x equals negative 4 must satisfy the equation. We plug it in and solve for a. Step 2. Substitute a equals negative 21 back into the quadratic. Step 3. Compute the discriminant b squared minus 4ac to prepare for the quadratic formula. Step 4. Use the quadratic formula. Then simplify to get the two roots. To build intuition, let's quickly glance at the graph of the final. In this example, we will start from a rational equation in x and show, step by step, that the resulting quadratic always has two real roots. Step 1. Combine the two fractions over the common denominator. Step 2. Multiply both sides by the product x minus a times x minus b to clear the denominator. Step 3. Expand both sides and bring all terms to one side. Left side becomes x minus b plus 2x minus 2a. Right side becomes x squared minus left parenthesis, a plus b right parenthesis x plus ab. Step 4. Identify the quadratic coefficients. Here, little a equals 1, little b equals negative of a plus b plus 3, and little c equals ab plus b plus 2a. Now, compute delta, which is b squared minus 4ac. Since delta equals a perfect square plus 8, it is strictly positive for all real a and b. Therefore, the quadratic has two distinct real roots for any not equal to b. A perfect square plus 8. It is strictly positive for all real a and b. Therefore, the quadratic has two distinct real roots for any not equal to b. In this example, we will prove a clean, discriminate fact about quadratics. For any quadratic ax squared plus bx plus c, having real roots is equivalent to the discriminate being non-negative. That is, delta 1 equals b squared minus 4ac is greater than or equal to 0. This is our only assumption. Now consider the new equation, ax squared plus 2, bx plus c plus m times ax plus b equals 0. Expand and group the x terms to place it in standard form. We get ax squared plus x times the quantity 2b plus m a plus the constant mb plus c equals 0. The discriminate of this new quadratic is delta 2 equals the new b term squared minus 4 times the new c term. That is, delta 2 equals the quantity 2b plus m a squared minus 4 times the quantity mb plus c. Let's expand delta 2 step by step. The quantity 2b plus m a squared expands to 4b squared plus 4 m a b plus m squared a squared. Subtracting 4 times the quantity m b plus c gives minus 4 m a b minus 4 ac. The mixed terms 4 m a b cancel, leaving delta 2 equals 4b squared minus 4 ac plus m squared a squared. Compare this with delta 1. Since delta 1 equals b squared minus 4ac is at least 0, multiplying by 4 preserves the inequality, for b squared minus 4ac is at least 0. Adding m squared a squared, which is non-negative, keeps it non-negative. Therefore, delta 2 is greater than or equal to 0. In this lesson, we will prove that a certain quadratic equation has two real roots, and we will locate them between three ordered real numbers. Here is the problem statement. To build intuition, let's place a, b, and c on a number line, in that order. We'll use this picture later for sign checks. Method 1. Expand f of x to reveal its quadratic form. Identify the coefficients a, b, and c. Then write the discriminate, delta equals b squared minus 4ac. This form does not immediately guarantee positivity of the discriminate for all a, b, c, so it is not the cleanest path to a proof of two real roots. Method 2. Use the intermediate value theorem through sign checks. Evaluate f at a, f of a equals open parenthesis, a minus b close parenthesis times open parenthesis, a minus c close parenthesis. Evaluate f at b, f of b equals open parenthesis, b minus c close parenthesis times open parenthesis, b minus a close parenthesis. Multiply f of a by f of b and determine its sign using a less than b less than c. Therefore, by the intermediate value theorem, there is a root between a and b. We mark that root as x1 in the open interval a comma b. Next, evaluate f at c. We have f of c equals open parenthesis c minus a close parenthesis times open parenthesis c minus b close parenthesis. Consider f of b times f of c and determine its sign. Since the product is negative, another root x2 lies strictly between b and c. Putting these together, we have one root strictly between a and b, and the other strictly between b and c. That is, a is less than x1, less than b, less than x2, less than c. Therefore, the equation f of x equals 0 has two distinct real roots located in those intervals. In this lesson, we will prove a powerful result about quadratic equations. Here is the problem statement, written algebraically, and the goal we want to prove. Step 1. A quadratic has two distinct real roots if and only if its discriminate is positive. 4x squared plus ax plus b. The discriminate is a squared minus 4b. Since the roots are distinct and real, we have a squared minus 4b greater than 0. This inequality will be our key fact. Step 2. Now, consider the second quadratic in x. Its discriminate, as a function of m, equals open bracket 2 times a plus m close bracket squared minus 4 times 3 times the constant term m a plus b. We simplify carefully and factor out a clean expression. Step 3. Notice that 1/4 of the discriminate is a quadratic in m, namely m squared minus am plus a squared minus 3b. To guarantee that the discriminate is positive for every m, it's It suffices to show this upward opening parabola is strictly positive for all real m. A quadratic alpha m squared plus beta m plus gamma is positive for all m if its leading coefficient is positive and its discriminant is negative. Here, the leading coefficient is 1, which is positive. So we check the discriminant with respect to m. Compute negative a squared minus 4 times 1 times a squared minus 3 be less than 0. After simplification, this becomes a squared minus 4 a squared plus 12b less than 0, which is negative 3 a squared plus 12b less than 0, or equivalently a squared minus 4b greater than 0. But that is exactly our key fact from the beginning. Therefore, the quadratic in m is strictly positive for all real m, and hence the discriminant of the second quadratic is positive for every m. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.